thank you everybody for coming. It's good to meet so many of you for the first time in person. I know this may be the first in-person event for a number of people. So we thank you for coming. For those of you that don't know me, I'm Stephen Esmorky. I'm the director of SC Aerospace, and we're so pleased that Suzanne and the SC Fraunhofer USA Alliance wanted to partner to put on this event and invite our cluster. And thank you to Dr. Bayumi for helping to organize this and bringing us and letting us visit the McNair Center. But that's all that I have. So I'm going to hand it over to Suzanne because this is really good stuff here.
Okay, thank you. Good morning.
Good morning. Good morning.
So this feels a little bit like deja vu to me because I was just here with the review board of the South Carolina Fraunhofer USA Alliance back in September, and we were so impressed that day with what has been done within one of the projects that the Alliance, and I'll talk you through this a little bit, has done, that we said we really should not keep this to ourselves. We should show this off. And so Stephen Estemborski is the director of SC Aerospace now at the South Carolina Council on Competitiveness. And I talked about this, and he said, well, why don't we, kind of use one of our next quarterly meetings, and we can show it to the aerospace community in the state. And we love that idea. So thank you all for being here. We're glad you're interested in this. I think you will find it very impressive. So just a little bit about the South Carolina Fraunhofer USA Alliance. You see 3 different logos here by design. We've included them all. The Council on Competitiveness is a nonpartisan 501c3 in the state that's focused on improving the competitiveness of entities within the state of South Carolina. We do that through educational programs, running industry clusters like SC Logistics and SC Aerospace, but also through applied research. So if you see things in the press that talk about the size of the aerospace industry and its economic impact in South Carolina, for example, how many jobs are created and what it means to our economy, those kinds of research statistics and data are coming out of our organization typically. So when the governor is quoting them at events, we kind of feel proud that those came from us. And the South Carolina Department of Commerce has a partnership with the council in a number of different areas, but in particular, they asked us back in March of 2019 to run a partnership, manage a partnership, and grow an initiative within the state of South Carolina that incorporates capabilities that exist within the Fraunhofer network. And I'll introduce you to that just a little bit. So I have an automotive background. I spent 20 years in automotive. Much of that time here in South Carolina as well. And 5 years ago, when I came to the council, I started as the director of SC Logistics. So I have an automotive and logistics background, but I also worked in Germany for 10 years. And I think when they looked around the room and said, who can pronounce this? I was, the only one. So here I am. But what we're trying to do with this initiative is it's a very sincere commitment on the part of the state, in particular the Department of Commerce, to trying to improve competitiveness of entities by working with collaborative teams that consist of alliance partners like the University of South Carolina and Clemson University in our state and Fraunhofer Network to do applied research projects. And that sincere commitment in particular looks like matching dollar for dollar. So if you are a company today that's interested in doing something based on what you see here, please see me or my colleague Marcel Schaefer, who just moved to the state from Fraunhofer in Maryland, because we would love to talk to you about whether a project that you might be interested in doing would qualify. If you're a South Carolina-based company and you're interested in doing something with these exceptional people here at McNair, please talk to us. We would love to help the Secretary of Commerce spend some of his money. So what is Fraunhofer? Fraunhofer is, by any standard, really the largest applied research network globally. Today, they have more than 72 institutes and 27,000 researchers and scientists around the world. Typically, where you're seeing these little dots, there are alignments with universities. They like very much kind of the, I think, cumulative effect of being engaged with universities where you have talent creation and education and basic research, and then they like to focus on applied research as well. So what is different about our model is these dots also typically are narrowly focused. So there will be like one technical area. It may be nuclear reactor safety, or it may be laser applications or something like that. And our model here in the state is much more exclusive. So we are really inclusive in terms of having more than one university partner at the table, but also exclusive in that we are focused not just on one technical area. We'll talk about that just a little bit. And about 25, 30 years ago, Fraunhofer decided, of course, the North American market is of interest as well, and they started to bring some Fraunhofer centers and institutes to the US. They started originally in Michigan with those efforts. A lot of that is based on Fraunhofer's strong connection to the automotive industry in Germany. But you can also see that, you know, the others, aside from the office in San Jose, California, have been located in the Northeast. So we're excited that the only, you know, there's this big empty space in the southeastern region of the United States and the Midwest, the rest of the Midwest, where there have been no Fraunhofer partnerships or alliances. So we're very pleased, and we feel like this distinguishes South Carolina in a positive way to have this alliance here. And I mentioned already, you know, we have not just said our entities can benefit from working with one center in one narrow topical area. We can actually apply those state matching dollars for work with any of the centers that you see here. And I've just taken little snapshots of the kinds of you know, descriptions that you would find for these. Again, this is something you would, you know, really talk to us afterwards. It's hard to, you know, it's a lot of information all at once, but Marcel and I can walk you through this. The center that we've done the most work with to date, I would kind of call them our pioneering partner, has been the Center for Experimental Software Engineering. And these are the kinds, I don't need to read this to you, but these are the kinds of capabilities that this center has. These are the types of expertise that they would bring to a collaborative team. And they were also involved in the project that you're going to see this morning. So in particular, it's this project here. You might notice too that it also says Clemson was involved. So people are sometimes surprised to see that Clemson and the University of South Carolina can work together in a collaborative team. They do. I think Dr. Srikant Pilla may be on the Zoom. So yes, this is another thing that we like very much about this alliance is that we're always looking for, you know, the pockets of excellence within the university landscapes within the state and putting them together for those synergistic collaborations. And you can also see, I just recently pulled this information together for our board. Since April of 2020, we've matched about $1 million in industry funds. That means companies like the ones that were involved in this project have come to the table with cash, and our contribution to match that dollar for dollar is about a $2 million portfolio since 2020, despite pandemic and so forth. So we're kind of excited about being able to see the light at the end of the pandemic tunnel. We think that companies are really, you know, kind of able to stop thinking about some of the pandemic-related things and start thinking about applied research again. So I would just, you know, offer that we will be here all day, and we look forward to talking to you at the breaks and over lunch and so forth. Both Marcel and I are here to answer any questions about that. And we want to go ahead and get started with the presentation. So I'd love to introduce Dr. Abdel Bayoumi, who is a professor in mechanical engineering and biomedical engineering and is the executive director of this McNair Aerospace Center. Abdel?
Thank you so much. Good morning, everyone. Welcome here. By the way, if you look at my gray hair, you can say I already been vaccinated, and I'm okay to take my mask. Not okay, but just to, with my accent, I don't want to make it difficult for you to understand. We welcome you all here, and this really, I never leave any chance without learning about who we are and what we can do. And before we start our presentation, I would like very much to give you some ideas about our McNair Center. Just very quick, that started 2013, and this is named after our native South Carolina, Ronald McNair. And the focus was on composite materials on about 15,000 square feet. But the mission, clearly, from the beginning, is how to help the state in advance in economic development, in human training, in education, around composite material and aerospace. Then all the initial activities from 13 until 2018 were around all types of design and manufacturing. And I will give you a quick idea. The presentation today is not really long. It's short and sweet because we want to tease you. Then you can come back quickly and say how we can be part of this. In 2018, we added 20,000 square feet for lots of activities. Like this area we are in today, it is actually started in 2018 with another 20,000 square feet. This includes lots of labs, lots of areas. One of them, digital transformation, and you have the opportunity through this program, and also the tour, you will see some ideas. But the new area covered digital transformation, unmanned vehicle, drones, 3D metal printing, and compression related to aerospace. And a quick look in here. I came originally, this is a long time ago, from North Carolina State. If you are familiar with North Carolina State and the Centennial Campus, is really the model to have a floor research space where you have everything, really one floor of company, another one of university, and they working side by side. McNair to us is that environment, is this type. Really we encourage investors to come to work with us. Through the last few years, we demonstrated that we have companies that will be here for 6 months, 9 months, working with our scientists, sitting side by side, using their equipment, compare ideas, and that is the environment we want to create. If you look at from in general here, you see lots of industry scale equipment. At the same time, we are not only show and tell for the equipment, we have lots of very specialized labs where actually we can use it for research. That includes our digital transformation lab in both sides of this room, talking about unmanned vehicle, we're talking about metal and additive manufacturing, 3D printing. Also, we added Factory of the Future that a few months ago, and you will be able to see it. And what we are trying to do here is really having all these labs working with each other for a common purpose. And you will see a good example of that in this particular project. If I come here, this is what I talked about. But I want to get closer a little bit for this project which Suzanne really introduced. We have multiple centers, 5 centers under McNair, to try to get all these centers working together to solve a common problem. Because if I join the industry, I'm not a mechanical engineer or aerospace engineer or biomedical engineer, I'm an engineer, where really I'm focused to solve the problem. And this is the training we want to get to our graduates. If you look at McNair in general, one area, if you group them around the design of a product or of a concept of technology, you see we have lots of activities related to design. Additionally, we have lots of also, if you group them around materials and technologies related to material design, manufacturing, and operation, then we have lots of areas. If we think about it from digital transformation, we have also most of known tools from machine learning to IoT to digital twin and you name it. Now, by combining each of these two together, you can focus on modeling and simulation. You can focus on experimental work. You can focus as well on predictive analytics. And this predictive analytics is close to my heart. When you came this moment, you saw this nice picture. This is how we learn, how really to get information, integrate information, predict what would be the behavior of this piece of equipment under different scenarios. If you look at all these, basically 6 segments here based on how you group them, this is really what we're talking about related to the project we are going to introduce you. And this is some statistics just for you to see. We have about 30 different faculty members from across USC, mostly from the College of Engineering and Computer. Not all of them housed in this building. We all have our own department, but we are connected through research in and under McNair. We have, before the COVID, we had like traffic here about 200 to 250 students. And we never, by the way, all this period, we never stopped coming here and work in our labs for, under this COVID-19. But let me tell you more focus on what technologies we try to integrate. This is our common machine, which it is automated 5-based. When we got this machine, it was like 6, 7, maybe 10 years ago. With the technology 10 years ago. And for us to be in research community, we need to advance. This is several $1 million piece of equipment. We do not have several $1 million every 10 years. Then we need to think. Then we have lots of areas really we need to research on, from design optimization to process planning to materials and everything we give. But we might be handicapped because, again, maybe we are not at the cutting edge of something else. Then we can go and buy all these digital tools to help us. But we're lucky enough. We built this digital side from our experience of 20 plus years with US Army, which is this side of the house, where you actually take the Apache, which is designed and built in the late 70s. But when it was provided to the Army, was nothing but the skin, the drivetrain, no skin around it. Then this machine is still in use until today. And the reason it's still in use is really how you extract data, different types of data, which is design and manufacturing from the OEM, sensing, you put it in the aircraft to detect vibration and other operation, then how to fly it and the business operation. It's like you are in your kitchen, integrating, basically mix all the ingredients to make a recipe. And that's what we did. We built all these tools with US Department of Defense, basically to have a methodology. Or we end up with what is known as CPM, condition-based maintenance, then predictive maintenance, where you actually make this recipe to develop an algorithm use it to predict the behavior of this piece of equipment, and this is the reason it's really going flying and flying and flying. And from our experience, we saved the army tons of money to do that. Then this is the other side, which we are into it. And the goal of this project, supported by Fraunhofer Alliance, is really how to help us really integrate this, move forward, and we end up with a machine that we can use really for the future. And this arrow here is this grant we got from Fraunhofer USA, integrating this. Move forward, our objective were really three of them. Enhance this piece of equipment for better process. This is not in competition with the OEM of the machine. This is actually in collaboration with the maker of the machine. In addition, we have other technologies, like the heater on the head itself from another machine, which I here representing this company, and that bringing different companies for different purpose to create a state-of-the-art technology. That it was our goal in here. And define, refine all these processes. How you really building a piece of composite material. We have faults. The whole idea is how you connect the fault to the processes. How you connect it with the actual materials used in the design. Means the product here will be actually input for the designer, for the manufacturer, for everyone to say, how can I improve in this? And third here will be the overall improvements, which really I don't want to bore you. You can insult you to read, but mainly how you integrate different technologies to solve today's problem without really investing. If I'm an industrial like yourself, I have an assembly line. This assembly line is on. You have a mechanical system. It's wearing out. This wear is affecting the quality of your final work. How do you relate this to that? Means if I produce a product 2 weeks from today, might not be exactly the same as a product to produce a year ago, because the quality of the machine is there. And this is what I'm trying to do, is really how you integrate all this sensing and everything into legacy piece of equipment to make it smarter. And the key word here, a smart machine. Okay. Just to keep this somewhere. Then I went at this point, dig little bit deeper into what we did. We have a team, this team of McNair Aerospace Center, Clemson University, people from who are attending this workshop remotely. Also, their expertise in materials. Fraunhofer USA from Maryland, where their software and artificial intelligence, all of us working on this for the last, I think, 8-9 months, meeting every week. Then we moved to every other week, and here how we collect all the brains around one problem. And this is the best example of concurrent engineering. Meaning really you get the resources as a time need. At this point, I wanna give Evan here little bit talking about maybe diamond sense on what we did in one shot.
Thank you. So, hello everybody. My name is Evan Barnett. I'm a research associate here at the university. I've been working on vectoring these things for I think about 3 or 4 years now. And it's been a real pleasure to be on this project, helping with the McNair team, as well as with the guys at Clemson and Fraunhofer. So to give you a little bit of overview of what we're looking at here, we wanted to guide you through the roadmap that we took specifically for our AFP machine and the process that's involved with that, but also give you a generic idea of how this can apply to other industry as well. So starting with our project, we have the DOC Advancing AFT project. That's what we're in. We divided this up into two systems. So we have the physical system, which is led by that wonderful gentleman back there, Burton Rhodes. And then we have the digital system, which is led by myself. We split this to understand how we're going to advance this machine. Obviously, if we don't understand the physics and the process parameters that are going on, we can't use the digital tools that the Center for Predictive Maintenance has developed to assist the machine. As well as if we don't use the knowledge and everything that Burton and his team have, we don't understand the physics and how we can use those digital tools to make the process better. So starting with our physical system, the first thing that we wanted to do was take a look at our machine. What are the sensors that we have on this machine? What's the data that we can generate? What's the important data that we can extract is from the process itself? And how can we begin to quantify and clarify that to get a clearer picture? As we continue to move on, there might be some areas that we have that we're having a gap. We might need to install some new sensors. We might need to look at how we can do some integration of new components, specifically like the Barnett heating unit that we're looking at, and get all of those into our machine so that we have a good starting point and understanding of all the physical processes and things that are going on. As we continue, we'll look at the implementation of new hardware as well. We had to get a little bit up and running here at the McNair Center specifically to get all of the digital tools and machines and everything integrated together so that we're able to then have that good starting point and foundation that we want. After that, we have all of these sensor outputs. We need to capture them and understand them and continue as we continue to move through that. We'll take the acquisition of the machine parameter data. Those are those specific key points that we're talking about, the most valuable ones that we can see, and then be able to actually take that and give us an idea of the predictive analytics of our quality of our product that we're putting out. Specifically in our case, that's going to be a laminate, that's going to be a composite structure. It can be tons of different geometries, as we'll see in some of the demos and everything. But obviously we need to understand how that's going to correlate and how the quality of that part is going to be taken out. To do that, we're going to move over to our digital side. Now our digital side, the first thing that we wanted to focus on was we have all of this data up here, as well as a lot of macro level data that might not be shown in this chart, but it's still very valuable to us. So we wanted to begin to organize and take all of that data so that we have a good way of understanding what process parameters are where, how we can begin to understand that, and also showcase that we can do this on legacy machine tools. A lot of the new and current control systems that you'll see out in industry have all of this technology built in. But how can we save money? How can we look at taking all of this data and extract it from a legacy unit? Additionally, we need to understand our quality of our part, and that is where the Ingersoll Axis system comes in. This is going to scan a surface profile of our part, where we can see defects and problems that may be occurring in our structure. Once we have all of this data and information, what we need to move on to next is how are we going to present this information that we're taking on? And this is where we call our deployable tools. These are things like augmented reality, virtual reality, digital dashboards, everything that's involved with those, and we'll see a couple of use cases in a second. As we continue to move further, what we want to be able to do is take those deployable tools, and we need something to model this. We need to actually be able to showcase, okay, how can we take the processes that are going on and be able to take them in and present them to an operator so that they know exactly what they need to do right away. Additionally, how we're going to actually connect that is going to be the physics-based dashboard. We'll have all of those data and deployable tools integrated into one. This is not just based on the data that we're finding from the digital side. This is from that physical system understanding that we have of the process so that we can continue to work and develop something that is presented not only to operators, but everyone involved in the automated part replacement process. After we collect and put everything together here, we have sort of a cohesive mechanism of saying, okay, we have the physical system, we have the digital system, and that's going to end up in our digital twin of our AFT machine. This takes all of the physical parameters that we have, blends it with the computational modeling and deployable tools and visualization that we can have, and be able to show us an actual digital twin of the machine that's operating. So, how we actually went about and did this, we wanted to show you a couple of use cases that we're looking at on this project on specific areas to give you a better understanding. So we'll start with 4. This is going to be our top one here, which is our first. This is our thermal model that was worked on by Chase Murray, Saeed Farahani from Clemson, as well as Srinivas Pella. Those guys did a wonderful job of taking the information that we got from our commercial partner Heraeus Novolite with the new HUM3 heating unit and be able to quantify all of the variables that are involved in this. So this is the angle of the crystal, the shape of the crystal, distances, all the operating parameters of the specific heating unit, which is voltage, frequency, pulse width, all of our parameters that we can involve and be able to create an analytical model. And so this is that traditional engineering mindset of we're going to have some mathematical equations, some computational modeling, because we understand that as part of the AFP process, this is a very important crux. We need to have good heating elements so that our fiber is then laid down onto our machine. Burton and his team have done a great job, and lots of other people out there of characterizing how heating can be a very, very big part of the fiber placement process. And so they're continuing to work on this as we continue to develop and look more at the actual heat output of the new HUM3, as well as how we can computationally modify that and validate that with sensor data coming from the machine. So one of the problems that we actually notified was we have a good understanding of the thermal side. We know that that is a specific process parameter that's going to be very valuable in how the AFP process works. But what if we have other correlations that we're not aware of? How do we know and can guarantee that defects might not occur? Or how can we know and understand that specific process parameters might be related to one another? So this is where we partnered with Fraunhofer on this project, and specifically Rohan and Arjun from there. And we wanted to look at how we can take all the data that we're getting out in a machine learning sense and be able to draw conclusions between operating parameters and quality of the part. So we'll start down here with our machine operator. He is in charge of manufacturing composite panels on our Lynx AFP machine. We'll come over here. This is going to be our input to this first part of our model. These are our parameters, the thermal behavior that we can see, our environmental conditions of the room, machine motions, things like feed rates, compactions, velocity, everything that's involved with our specific AFP machine over there. Our output from this phase is going to be a surface profile. I've talked about the Ingersoll inspection system earlier. What that will do is it will basically scan a part and we'll be able to look at the surface profile to see if we have defects. You can see here we have a toe missing. There's a gap between those two. And for example, that's one of the defects that we're looking at. Fraunhofer looked at creating an AI pipeline that will actually take images based on previous defects that we have and be able to analyze and extract them from this phase so we can see all where our defects are. In addition, also the location of those specific defects within our part. From this point, we're going to move into sort of the pre-processing of the real world. So this is where we take the input data and we take the output data and we're able to correlate why defects are occurring with the process parameters that exist. Maybe our feed rate's set a little bit too high and we can try and figure out how that's going to adjust and take into account for our problems. Maybe our heater settings are incorrect. Maybe it's a hot summer day in Columbia, South Carolina, and it's 99 degrees like it always is. And that's causing us to not have material stick to our manual. This is where that model is going to be able to identify and understand those correlations without human input. It's going to take all of that information, look at it, and draw connections between the two things, or three things, or multiple things that exist out there, and be able to then put us into a pre-processed database. All of this information will be available to operators and researchers within the project, as well as we move down into this bottom part, which is actually going to be our information that's going to be presented to the operator for defect mitigation, or as well with some of the new units, we can actually directly control the machine and the parameters that are running there to avoid defects. This is done by looking at the previous slides and the defects and machine parameters that we found out of those, the operating parameters of the current ply that we're in, and how those are going to affect. That will lead us into our defect prediction, and like I talked about, will lead us into how we're going to take this and present it to people or directly control the machine for mitigation of these defects and the quality of our part. This is going to ensure a larger and greater scope of our project, not only within fiber placement, but within many manufacturing realms. Our final one that we'll kind of move into is the digital tools of our project. This is where we took all of that data and we're able to showcase how we're going to move and look and present all of this data to our operators. So we've created things like digital dashboards that show trends of all of the machines, not only our AFP machine, but all the machines related to composite manufacturing in our facility. We've created augmented and virtual reality training. One of the areas that's specifically on AFP machines is interesting and intricate is actually cleaning the head So up here you can see on the left is our actual AFP machine. This is a virtual representation of it, and this is an operator taking apart and cleaning the head. And we'll be able to see a demo of that a little bit later on. As well as augmented reality, so this is a specific one that we wanted to showcase. Okay, how can we take augmented reality glasses and present information to the operator that's relevant, but also make them a key part of the system in providing information back. Sometimes we need to be able to monitor and produce parts very quickly. How instead of scanning with the access system, if an operator can see a defect in a part, he can log it right away on the glasses and then keep running as well after he fixes that. So all of these deployable tools are based on the data and everything that we have coming out of the previous setup. This is where we're presenting all that information to the people that need to know it, but also in the way that they understand it, which is a very, very key point when dealing with all of this data that we're collecting. Finally, the thing that we'll move into is our digital twin. And so this is where we're taking all of that and being able to represent all of that information that we're gathering within a real-time sense. So we'll go on to the other side in a little bit, and we'll be able to see this actually happening live. But these two machines, or what we have our AFP machine here, and then our inspection robot as well over here. Both of those will move corresponding to the real machine. The heater and everything will turn on just as we have it. And this is where we can present information back to operators like you can see up here of the part that we're running, the layer and the course that we're on, as well as specific parameters of how fast the machine is moving, the mode that it's moving in. And we also can provide direct control back to the machine from an interface like this to where we can trigger an emergency stop if necessary, or we can alter specific process parameters that might be of interest. So after we continue all of that, we wanted to showcase how that digital twin impacts our AFP process, but also into the larger scope of the programs, not only in South Carolina, but nationwide. And so I'll hand that back to Dr. Ramey so he can educate you guys a little bit more on what's involved in that. Sharing.
You see now why we really are excited about automated. I really love it when I see someone like Burton or Evan. She's really breathing, being part of it. This is a type of training. And this girl here is back, graduated last year, and we are very proud of her. Meaning here, this is we can proud. Really are very proud of freedom to give ours. We move quickly here. Really, the first outcome we have achieved is not only we have a machine, state of the art now, to be a test bed for more research. We established a framework that you can take it and apply it on the industries. You will get a chance behind you here, you will see lots of case studies where we take that methodology or framework and apply it to different industries, even outside engineering, like health and nursing and all. And this is the most important thing we achieved. And this in less than a year, but we focus in very specific use case to demonstrate everything and all technologies and all tools. The achievement, I think, in my measure, I think we were successful to meet the goal from the beginning, to have the framework, to advance safely, to be partner with our industries. The other thing which really benefits. This benefits, besides education, besides research, it is benefits to advance and to be the owner of all technologies in our industries. That is the most important. I want to get you here to watch really a video that this is the latest version of it. And this will give you a flavor. It is only 4.5 minutes, but will give you an overall view of the whole project, starting with entity.
Researchers at the University of South Carolina's McNair Aerospace Center, led by Director Abdel Ayoubi, have been hard at work advancing the state-of-the-art in automated fiber placement, or AFP. The multi-institute interdisciplinary team is currently collaborating on a program funded by the South Carolina Department of Commerce through the South Carolina Fraunhofer USA Alliance. This partnership leverages the expertise of the University of South Carolina's McNair Aerospace Center, Clemson University, and Fraunhofer, USA, and couples South Carolina research institutes with partners from industry for the purpose of developing solutions to complex manufacturing problems. At the outset of the 2020-2021 Advancing Automated Fiber Placement project, our team primarily focused on developing a framework for digitally transforming the manufacturing process. This framework would harness existing process parameters and sensor outputs to be used within a dynamic predictive model. Our proposed model was tested and used to improve the layout quality of advanced materials. Specific elements of the digital transformation framework include virtual reality, VR training, augmented reality, AR dashboards, and a digital twin. The digital twin provides a real-time visualization of the system, defect prediction and prevention, and system analysis. The development of the physical framework is led by Burton Rhodes, while the development of the digital transformation framework is led by Evan Barnett. Using digital transformation, the Advancing Automated Fiber Placement project's outcomes leverage machine learning techniques in order to rapidly analyze new, advanced materials for the purpose of optimizing layout parameters. The system anticipates machine-operated parameters, material properties, heater parameters, environmental factors, and inspection data. Through this AI training, via an advanced machine learning system, key parameters are determined for prediction and prevention of defects during fiber layout. Now, continuing from the Advancing AFP project's midpoint review, our team has made significant advances in several research areas, including the development of an analytical thermal model, the integration of additional sensors and actuators, the refinement of augmented reality operator dashboards, the organization of data from the legacy controller and inspection equipment, and the integration of the hum-free intelligent heating unit from Gray's Nobelite. Each area has contributed to strengthening this new dynamic digital twin for automated fiber placement. This digital twin seamlessly blends machine process parameters and analytical thermal behavior models with inspection